Hello, and welcome to this webinar. My name is Emmanuel Tovic, and I am the lead developer of SIMBA. I hope everything is all right and you can hear me. I will assume it's okay. So again, welcome to this webinar about SIMBA and Python and how both can be quite helpful in the process of designing power converters. So the agenda that we have today is we'll start with a quick introduction of basically what is SIMBA. Then we'll dive in why do we need advanced scripting when designing power electronics converter. We'll have a review of the library, the Python library that we ship with SIMBA. And this webinar, the audience is targeted toward beginner or person who never heard of SIMBA or never heard of Python, just to understand what it is about and how that can be helpful. And we'll go over different, you cannot hear me? Is there a problem? Is there a problem? You can hear me, right? I just want to make sure. Okay, sorry about that. So, yeah, and we'll go over multiple case studies to illustrate this. And finally, we'll conclude and we'll have time for questions and answers at the end of the webinar. So I think it will last somewhere between 30 and 40 minutes. So let's start with an introduction to SIMBA. What is SIMBA? So SIMBA is a new power electronic simulation software with unprecedented speed, accuracy, and simplicity. That's nice, but when we said that, basically we said nothing. So what it is actually. So in these slides, we added all the steps that are involved in the design of a power converters that requires simulation. Okay, so everything starts with what we can call system design, where we do high-level calculations, where we can decide, and basically we start with specifications. So we decide the topology, maybe we can try different options, and we can run maybe power quality studies. We do thermal analysis, efficiency analysis, estimate the loss, optimize the design. We can do also reliability analysis. We can also use those type of calculation simulation to predict the lifetime of the power converter. So this is what we can call system design, or we can also call kind of pre-design, the pre-design phase. Then there is what we can call the control design, where we'll basically look at the, maybe we'll go and look at the transfer function of our system, look at the margin, the phase and gain margin, and from that calculate the closed loop and make the synthesize of the controller. Maybe we'll write some algorithm in C code. Maybe we'll go and build the controller of our motor drive. So those two steps here, this is where SIMBA is very good at. This is what this is basically the strength of SIMBA. Then there are other steps that are involved in the design of a power converter. There is everything that is kind of SPICE related, where we can design EMI filter, or we can just study EMI, where we design the gate driver, or we go down the component selection. This is what we call here gate driver and EMI filter design here. Then there is, of course, the magnetic design and also the controller software and hardware, where we can maybe generate code, or maybe we can write the controller code manually, and we can do also real-time simulation to make sure that everything works well. So this is those are stuff that we don't do, or that we don't do well, but that we plan to cover in the future. That's our ambition. Maybe we won't cover them natively. Maybe we will work with partners. For instance, we will never do finite element analysis in SIMBA. At least I don't think so. But we want to provide a complete platform for the simulation need for power electronics converter design. So SIMBA is not like the other tools. I think we have some very key points that differentiate us. One of them is SIMBA is not just software, a Windows software that you install on your computer and that you open and you use. There are multiple ways to use SIMBA. The first one is actually desktop application software, very conventional. But the entire SIMBA capabilities can also be used from a Python library, and that will be the theme of that webinar. And there is also an online version of SIMBA that works in the browser, and this online version makes it very useful for education and teaching needs, because there is nothing to install basically. So I don't want to go down the road of showing you all the features of SIMBA, but I just want to let you know that SIMBA is now maybe not feature complete, but the feature set of SIMBA is very large. We have very rich libraries, multi-physics libraries. We have a first-class solver for transient analysis and for AC sweep. We have a multi-time step solver. We have a lot of features that are hard to find in other tools. For instance, we have the capability in SIMBA to debug C code. So you write your C code, that model your controller, and you can debug the C code by adding breakpoints and seeing what's happening in your controller. Let me show you very quickly what the user interface of SIMBA looks like. So this is the desktop version of SIMBA. Let me put that away. And we try to make a user interface that is very clean, that doesn't need any training. Here I have different projects. Maybe I can, I can open this DAB here. So it's a DAB that runs at 250 kilohertz. And here we have our controller. We have some C code that we have written here that model or basically the controller of our C code. We can set here the settings of the simulation that are very simple. We have our own solver that we have developed, especially for power electronics, that we call the predictive time step solver, which makes it extremely accurate and extremely fast. So I can run here a simulation. You will see that now the code that I have here is compiling and the simulation is progressing. And I can look at the waveforms that we have selected. Okay, so this is just to give you a very high level overview of what is SIMBA. On top of that, so you can see that here, what we have in blue are basically the electrical circuits, and blue wire is an electrical wire. In green, the green wires are basically the control signals that are here. We have also the capability to model thermal circuits here in orange, and the capability to model electromechanical circuits, like for instance, if I open this PMSM drive, what we have in red here represents the mechanical coupling between the rotor of this PMSM and the load. So what's new in SIMBA? So the key point here is we know our development team of about 4 or 5 developers working on SIMBA, and we have, I think, a very aggressive roadmap. We try to release new version every trimester. So every 3 months, there is a new version of SIMBA with major features. So just in 2023, so since the beginning of the year, we have added a lot of features in SIMBA. We have introduced the multi-time step solver. So that's basically an evolution of the SIMBA solver for digital controller. We have added SIMBA Online. We have improved the DFT calculations. We have improved the motor models with the capability to model saturations. And we have added a lot of models in the libraries just in the first 6 months of the year, and we have more and more coming. Actually, the roadmap of SIMBA is public. It's available on GitHub, so you can have a look to it, and you can also request features if you want to. And basically, we'll study your feature, and we'll answer to you if we are or if we are not going to develop what is requested. Okay. So advanced scripting in power electronic simulation. So if you look at the kind of the traditional way to design converter that maybe not all, but many companies follow, it works a little bit like that. Of course, this is a little bit subjective. Of course, it's not always the case, but generally the process looks a little bit like that. Of course, it starts with a specification. You need to build a DC converter for that voltage and for that power. And from that, you can maybe start with an Excel spreadsheet or maybe with some simulation to try some topologies. And then from that, you will select components that gives you data sheet. And you kind of iterate between some Excel or MATLAB files and some simulations to get to a preliminary design where the topology is fixed, where the values of the component are somehow set. Then you go in the second phase, that will be a detailed design, where you will actually select the components, where you will design the magnetic, where you will design the heatsink and the cooling system. You will also select all the component values. Maybe here you will also design the PCBs and you will write the controller, and then you'll go down the prototype road. And first, we're not saying that this is bad, and we're not saying either that SIMBA will revolutionize that. No, but we think that there are some kind of issues with this workflow. First, it's kind of labor intensive. A lot of steps that are involved here are manual. Every time there is a change in the specification, or you need to repeat the entire process. And a lot of the time, the process requires you go in the software, you run simulation, you make some calculation, you export the result to Excel, you run other calculation, and you kind of iterate like that in a very manual manner. Of course, this process is very susceptible to human error, and if you don't have the prototype on the table with some measurements that kind of validate what you have simulated, the risk that you made a mistake is pretty high. And we've all done them. So how SIMBA improves this? So basically, using SIMBA and its Python library, the process of designing the converter can be automated or semi-automated. So what does that mean? That means that instead of going into the software and adding all the components from the library one by one and setting the values, you can automate this, like build me DC-DC converter with using a book topology and put a feedback loop with a PID with that and that and that values. So the design of the model, the design of the model can be automated. The controller itself can be also designed semi-automatically, where you can use this Python library to run AC sweep to extract open loop transfer function, and you can use some Python control library to calculate what should be basically your PID controller values, for instance. You can use this Python library to make intensive parametric and optimization analysis, such as sensitivity analysis, Monte Carlo analysis, to make sure that the design that you have is robust. Okay. You can also use it to run thermal analysis, as we will see in a moment. And finally, you can use this to automate the validation documentation. For instance, you can write tests to make sure that the specifications that you have at the beginning are met. And you can also generate the documentation, like for instance, the BOM, or you can do basically everything that you want. Another thing that is very, very important is, in a lot of the case, the converter design workflow, the workflow rely in the head of the engineers doing it, right? So using SIMBA and its Python module, the workflow, the entire process is actually saved in just 2 files. There is, of course, the SIMBA project files, where we have the data about the circuits and the component values, and also with the Python scripts. And these scripts can be saved and it can be versioned. This is something that we do a lot in computer science, where you have script version 1, and then script version 1.1, we have added some requirements validation tests. In version 1.2, we have changed the values of the filters to match the European EMI limitation, and so on. And one of the advantage of that is if the engineer who designed the converter basically leave the company or leave or is doing something else, the process, the workflow is still saved somewhere, and a newcomer can come and look at it and improve it and understand how it works. So to arrive there, we have to learn a little bit of Python. So what is Python? Python is an accessible and powerful scripting language. Accessible because it's free. There is nothing to pay. Everybody can go in python.org and download it. It's very easy to learn. Python is well known for this, even for non-programmers. So if you have ever written a MATLAB script, the level of difficulty is the same thing. So if you know how to write a MATLAB script, you already know how to write Python. One of the advantages of Python over MATLAB is, okay, of course it's free, but also it's extremely versatile. It's not only for engineering. It's also used in web development or data analysis, and of course, machine learning. So if you want to build websites where the data that you have on the website relies on SIMBA calculation, you can do it. If you want to do machine learning where you train the machine model from simulation, you can use Python and isim.simba module. Python is well known to have a super vast collection of libraries and modules that you can download for free. And a lot of them are very good for engineering tasks. There is NumPy for numerical computation, Matplotlib for data visualization. There is SciPy for optimization and scientific calculations. There is one that's called Control, just for control design and system control studies. And finally, automation. Using Python, you can automate everything, as I was saying, like the design creation, the report, the tests, so everything that you basically do step by step with your Excel file can be automated. Okay, so how to get started? First, you go in python.org. And from there you can download Python. So Python is not like MATLAB, where the language and the software that you use to code the language are the same. Python is the language, and then you need to select software to write and run the code. My recommendation will be to go with Microsoft Visual Studio Code, which is free and open source, and that's very powerful, but there are other choices. And of course, if you go on our website, simba.io, you can look at, we provide the documentation of our module and a lot of examples and tutorials to get started. So let's start with a very simple case that we have here. Just to show you, so this has nothing to do with SIMBA, this is just like pure Python. I will zoom a little bit. So right now, I'm in Visual Studio Code and I have opened a Python file that I've written, a very simple file. So the first thing here is you see those import lines is where we will import libraries that we want to work with. So the first one that I have selected is NumPy, which is basically a numerical calculation modules that we use to create, whenever you want to create large arrays, it's a good choice to go, or large matrix, it's a good choice to use NumPy. And Matplotlib for data visualization. And here we do something very, very simple. We create a variable f, and we assign the value 5, and f represents the frequency of the signal. So to write a comment in Python, we use this $. Then we create an array x, that goes from 0, where the values go from 0 to 1 with a step of 1 milli, and this basically represents the time. And then we create another array y that will be basically the sinus of 2 pi f t. Okay, so here we create a sinusoidal waveform and we save the y and x values in 2 separate arrays. Then just to show you here, we calculate the RMS values of that signal. So it's just one line of code, and also we will plot it here. So let me debug this. So debug this, I will just go here and I will debug the current file. So you see it's kind of very easy. There is nothing to be afraid of. And here we can create the values while the code is running. We can look at the value. So we see, for instance, that x is an array with values ranging from 0, 0, 0 to 1, 0.002, and so on. And we have another one for y. And here we calculate the RMS value. The RMS value is plotted here, 0.7. You know, it's sinus of amplitude 1, so the RMS value is 0.7. And here we are plotting the curve here. And we have a nice plot view, and we can do everything that we want: histogram, bargram, 3D views, and so on. So this is just to illustrate how Python is simple. And how, if you come from MATLAB or even Excel, there is nothing really very hard to master this. So let me stop here. Okay, so here you saw that we are importing modules here. And one of the modules that can be imported is sim.simba. So sim.simba is a Python library. So sometimes I use module, sometimes I use library, but it's basically the same thing. And what is it about? So it's a Python library that is very easy to install. It's just one line of code. It runs on Windows, Linux, and macOS. It's completely independent. So it's not an API that will call the software. It's actually the software itself. So you don't need to have SIMBA installed to use this module. So if you want to distribute calculation on the cloud, you can just install it on Linux server where SIMBA is not installed. That will work. The documentation of the library is available on our website. We try to be as accurate and comprehensive as possible. And we also provide examples and tutorials on our website and on GitHub. So let's start with a very simple case. Okay, but what we can do with sim.simba. So to start, we start with this line where we import from sim.simba the classes that we want to work with. So for instance, here, if you want to create a new design, you will import design. Then from the design, you can actually create and modify the circuits. So for instance, here, I create a new design, I'll give it a name, and I add a device on that design that I call V1. I can assign a value to V1, so you see how the syntax is easy. And if I want, I can change the settings of the transient analysis. I can also run an AC sweep analysis here. And I can run an analysis. This is how we run an analysis. And of course, if the analysis, we can get the status when the analysis is completed. And if the status is error, I can retrieve all the errors that happened in the simulation. And to retrieve the result, I can just request the signal. I have different options. One of them is by using the name of the signal. So let me show you a very simple script again, but this time using sim.simba. So that's here. So here, let me zoom maybe a little bit. We will load the module sim.simba, and we will import the design examples that we provide with SIMBA. And I'm going to run this. Then the last thing is we are getting a new design that we call flyback converter. This is a design example from SIMBA. And this time I'm running it what we call an interactive notebook. That means that I can have on the left-hand side my code, and on the right-hand side, I can have the result of the simulation. So now you see I'm just creating a new transient analysis job at line 9. And at line 10, I'm just running the slide. Of course, it's not working. What I have done. I probably made a, oh, I have not run this cell before, sorry. Oof. So of course, flyback converter was not existing, so I just went to this one. And so now I just run the simulation. You see it's kind of instantaneous to run a simulation. Then I retrieve the time and output voltage of that simulation, and I can run the simulation here. Okay, so in like 4 or 5 lines of code, I was able to load a design, run a simulation, and get the results. And once I have the results, I can do everything that I want. So just to show you, the design that I'm running is actually this one here. Very simple flyback converter where we use idle switches here. Okay, but of course, we will not use such a module just to run, you know, flyback converter. So a very typical use case is that can be used to compare semiconductors in terms of losses and in terms of efficiencies. So SIMBA is compatible with the thermal description file that was first introduced by the software called Plex, and that is supported by a lot of manufacturers. So a lot of manufacturers like Infineon, Wolfspeed, you name it, on their website, you can download thermal description files that are XML file that represents the electrical thermal aspect of semiconductors. So that will basically can be used to estimate the losses from the actual junction temperature of the devices, from the current and voltage in the device. And we can use SIMBA to, of course, load those files, simulate them, and calculate the efficiency of the converters. And we can use the Python module to automate this task and to compare multiple semiconductors very, very seamlessly. So let me show you what it looks like. So all the examples that I'm showing are actually available on our GitHub. They are open source, so you can go and you can run them if you have access to SIMBA. So here I have a script that is called thermal data.py. I won't explain everything. I just want to show you this. So basically, we have a folder that we have called script folder, and in that folder, we have added a lot of different thermal description files from different semiconductors. And these are Infineon's IGBTs that we have downloaded from their website. And what we see, I'm lost. Yeah. What we do is basically for every file in this list of files, we run a simulation and we get the junction temperature at the end of the simulation and we estimate the losses. And from that, we plot an histogram. So let me run that for you. Run Python file, should be quite quick. So here we have about, I don't know, 10 IGBTs, and we can look at the results here. Yeah. So here we can see for every simulation, SIMBA was able to estimate the losses and the junction temperature. Of course, we can, if we want, we can extract, the difference between switching losses and conduction losses. We can look at the efficiency of the converter. We can do parameter sweep and change a lot of different values, but this is just to give you a kind of a high level overview of what we can do. And it takes, just a few seconds to run 10 to 15 simulation. Something that is very nice in SIMBA, I can show you here when you run this type of analysis, is we have an option here that we call stop at steady state. What does it mean? That when this option is selected, the simulation will stop whenever SIMBA thinks the steady state is reached. So that means that the temperature has reached kind of its final value. So for instance, here, if I go here and I look at the junction temperature, we can see that after about 2 seconds of simulated time, we have reached the steady state. So when we do this type of parameter sweep, even though the time constants might be different from semiconductor to the other, because maybe the size, the physical size is different and the thermal behavior is not the same, the temperature and the loss value that we will have will be the stable one, will be the steady state one. So this is just to give you one advantage, one usage of that Python library. Something else that we can do, it's a little bit more involved, it's a little bit more complex, is calculating the efficiency map of a powertrain. So a powertrain is basically, if you talk about an EV, you have a battery, you have an inverter, and you have a motor, in this case a PMSM. And the inverter itself has its own efficiency, right? And we can use the thermal description files from the semiconductor manufacturer that has just shown to estimate the losses and the efficiency of the inverter. However, in real life, the motor will never work at a single speed and torque operating point, right? It will, the speed and the torque will change. So the voltage and current will change, and we want to make sure that the efficiency is as high as possible over the entire range of operation of the motor. And one way to do that is to create a space of torque and speed values. And in this space, for every torque and speed values, we can actually calculate the ID and IQ quadratic current reference values, inject that in our model, and from that estimate the loss of converter. And by doing that, we can actually create a map like this, where we have the efficiency here that is plotted for multiple speed and torque values. This on my computer, that is a 10 core CPUs, takes about 5 minutes to run a little bit more than 200 cases, which is actually very good. And the reason why we can achieve this level of performance is in SIMBA, using the SIMBA Python library, we can actually run all the calculation in parallel. So we can use all the cores, and it's very, very simple to do that. And we provide examples again on our GitHub. So let me just show you very quickly how the scripts looks like. So I'm going back into Visual Studio Code. I'm going back to Visual Studio Code, and where is it? Inverter Efficiency Map, it's there. And you can see that the script is, it's about 200 lines long. So it starts to be a little bit complex, because we do actually have a maximum torque per ampere and flux weakening algorithm that are coded here in Python. So it's a little bit more complex, but you see the syntax is quite easy, for mathematical equations. It looks like a lot like MATLAB. And here we're running our calculations in parallel on all the core, and we can generate curves like this, as I was showing, where we have the efficiency of the inverter for different torque and speed values. And in this case, I think it's because the semiconductor we have selected are kind of oversized. The efficiency is extremely good. But we can change values like the gate resistance, the switching frequency, the bus voltage, the case temperature, and we can look at the impact of those on the efficiency map. Okay. Another example that I can show is about the LLC, the design of a LLC converter. We actually made an entire webinar on this, but since it was super interesting, I just want to talk about it also here. So the design of LLC converters, it's well known to be like a tedious task, because the main reason is it's a highly nonlinear system that doesn't have an analytical solution, right? Because the gain is function of the switching frequency, and everything is non-linear. That are some hypotheses you can make, like the first harmonic analysis that kind of simplify the model, but it's still an an hypothesis, and the only way to solve, and by solving, I mean to get the optimal design from the requirements, is with brute force. So to run a lot of simulations with different values and try to find what is the basically the best switching frequency and the best tank values. And with the Python module, we can actually automate this. We can run thousands of simulations in within a few minutes, not within a few hours, to try to extract the actual, the optimal design values without making strong hypotheses, just by running like full detailed transient simulation. So in this example, if we run about 8,000 simulations to cover the entire range of the entire space of design data, it takes about 6 minutes on my computer, which is probably very hard to achieve, in any other software. One of the reasons is, of course, the calculation of SIMBA are fast, but also because we can run all the calculation in parallel very easily. So that was what I wanted to show you. I'll finish now because it's already 40 minutes. So as a conclusion, first, Python. Python itself, I think it's a valuable replacement for Excel and MATLAB for many engineering tasks. We provide a Python library called sim.simba that basically can automate the design of power converters. It has no limits. I just shown a few examples, but basically everything that you need to do, not everything, but a lot of stuff that you might want to do can be automated with SIMBA. We provide a lot of technical resources to get you started with that, and we are currently organizing trainings that will happen in US, in Europe, and in India in September. I don't know if we have started to communicate on this, but we'll communicate soon on those trainings. And finally, I believe like SIMBA is just that. SIMBA is new. We've released it 2 years ago, and we start to have like a strong user base, but we still have a very aggressive roadmap with a lot of features coming up. So yeah, stay tuned. And I hope this webinar was interesting, at least. And if you have any question, feel free to ask them. Now it's time for the Q&A. So we have one question from Andre. Is SIMBA free license, or there is a price for it? So yeah, so there is an academic license that is free that you can get if you work in the in a university or if you're a student. For industrial application, yes, there is a fee. There are multiple license options that you can choose from. Thank you, Andre. Let me know if you have any other questions. You can use the Zoom Q&A to ask your questions. Question from Seri. Can this be extended from discrete device, IGBT is exactly like we have, to IC technology? Yes and no. So if you want, so IC integrated circuit. So if you want to build an IC, an integrated circuit, you can, some other softwares do it, and you can also do it in SIMBA. You can actually build like a, do we have any example here? You know, like a control block or a mix between control and electrical block, where that represents your IC, and from that you can, you know, optimize and run your simulation. So this is today, it's possible. In the future, we plan in supporting description language that will give maybe an easier way to model ICs. So the answer is yes, it's possible today, but that requires the manual modeling of the IC. And I think we have everything that you need in the next version. For instance, we'll have op-amp, which we don't have today, but they will be included in the version that we'll release next year. We have comparator, op-amp, we have basically everything that you need to model ICs. And in the future, will be compatible with description language to be able to model those. Question from Adele, does SIMBA support SPICE simulation? No, SIMBA is not a SPICE solver, although we are a descendant from SPICE, if you say. However, we are working on the way to import SPICE models inside SIMBA, and we hope to release that in the coming months. If you are if you have a more precise need, I will be curious to know about it. Other question from Mr. Anonymous. If I want to customize the converter design, how automation can help me? Do I need to write the script for the converter design? If you want to customize the converter design, so let's say here you have a converter. Okay, like any other tools in SIMBA, you can, you know, change the values, so you can customize it. And if you want to add components, you know, you can add whatever you want in the design. So you can customize using the graphical user interface. But maybe you don't know before what are the modification that you want to apply. And in this case, with automation, basically you can do large parameter sweep, or you can do optimization algorithm and this will require to write a script to basically improve and optimize your converter design. So I don't know if I have answered your question. Please let me know if it's not the case. Okay, let me know if you have any other question. Other question, what are the differences between Simulink and SIMBA controller implementation? Can you implement both analog and digital controller loop? So Simulink, so here I'm just talking about Simulink, no, not about SimPower systems and other module, but Simulink, it's pure, I would say, no, it's not pure digital, but it's pure control, right? While in SIMBA, it's a mix between control and power, or control and analog. So you can do both with SIMBA. Actually, in Simulink as well, but in Simulink, you have to know the analytical equations of your analog loop. Okay. How effective is this tool for EMI and parasitic calculation and estimation? As I was saying in one of the first slides, this is something that we will release in the first version that will be in beta, that we will release this summer, the capability to have detailed switching transient and to have EMI filter. Our target is to be as effective as LT-SPICE. Basically, LT-SPICE is a very good tool, and its main advantage is it's free, and that's basically our target in terms of capabilities. And yeah. Also, we don't plan in estimating the parasitic, for instance, the parasitic from the PCBs. This requires kind of FEA analysis, and we don't plan in doing that in SIMBA because you need the PCB, that geometry and so on. However, we plan in having the capability to import those parasitic values inside SIMBA. So thank you all for your questions. I hope this webinar was interesting. If you have any other question, please let me know. You have my email address here, and I guess we'll send you an email with to follow up. If you want to try SIMBA, you can also directly go on our website and give it a try. And that's pretty much it. So thank you again for attending this webinar. I wish you a very nice end of day and a nice summer. Bye-bye.